Okay, so let's go ahead and get started. Welcome to my presentation today on Basics of Nonlinear Analysis Explained. My name is Sashi Sitamaram. I'm a technical solution specialist here with CAD Dimensions. I work out of the satellite office in White Plains. So the goal of today's presentation is really to give you an insight to nonlinear analysis itself. So I will not be spending too much time on the nonlinear tools within SolidWorks. However, my goal is to show you when and where to apply nonlinear analysis, why nonlinear analysis is important, and some of the theory behind using nonlinear analysis. So I want to start my presentation today by showing you this picture here. So this is a picture from the 2010 Olympics, and you can see there Usain Bolt is winning the 100-meter race. A lot of us know about this race. It was very important to Usain Bolt. Now, one thing that many people do not actually know is that this guy right here, I don't really know his name, was actually projected to win. During the training sessions leading up to the Olympics, he had better time on average than Usain Bolt, and however on game day Usain Bolt seemed to have won the race, and apparently he won by 2% difference, which is in a 100-meter race. That is 10 seconds. That is almost quarter of a second difference that he won. Now the reason why I'm talking about this picture is because these two guys trained together. They probably had the very same nutritions and diets and exercise and workouts. However, what was the small difference that gave Usain Bolt that 2% win over this guy, the second place guy, which many of us don't know his name because he was not the winner. Now, we might never know the answer to that. However, this race reminds me a lot like the engineering world, especially when it comes down to simulation. When it comes to winning project bids or running simulation or trying to investigate your part or your assemblies, 2% error could mean you winning the project, or you're successful in building the part, or even being able to remove 2% material. It makes quite a bit of difference. So what really this picture signifies here is that many engineering companies have already started to adapt simulation, and especially virtual simulation, using SolidWorks, the simulation tools that we have in SolidWorks. However, a lot of companies try to stay away from nonlinear. They try to keep the linear analysis portion of it, and try not to dive into nonlinear. Well, in this presentation, I'll show you how important nonlinear can be in giving you that 2% edge to win projects and be able to dive deeper into your models and give you a better understanding of your models. So many of you might already know that SolidWorks has simulation software. And this is essentially what I was talking about in terms of many companies have adapted these tools here already. So under the SolidWorks simulation standard, and even the professional tools where they're using frequency and thermal, but not many companies have jumped into the premium tools that we have, such as the linear dynamics, composites, nonlinear dynamics, and nonlinear static. Now, when it comes to dynamic analysis, this might be a very specialized industry. But however, nonlinear really resides in many industries. You'll be surprised to see that many applications, many engineering applications are actually nonlinear, because nonlinear is actually real life. Um, every analysis can be simulated using nonlinear analysis, but not every analysis can be simulated using linear analysis. So I like to start by showing you the difference between linear versus nonlinear. These two pictures really summarizes linear versus nonlinear. You know, before people were able to explore into the world, explore into the universe, there was many assumptions being made that the world is flat, or the world is a circle, or the world was a cube. And again, these are all assumptions. So tying it back to engineering, a lot of engineering work requires assumptions. And when we break down the linear versus nonlinear, you'll see that when you run a linear analysis, for one, you are assuming constant model stiffness. So the stiffness in your models, in your assembly, does not change throughout the simulation. Secondly, small displacements and rotation. Now, there isn't really a number that signifies small displacements and rotation. However, what signifies a small versus a large displacement is when the displacement or rotation is so big that it actually changes the stiffness of your model. Third is the constant load magnitudes and direction. So when you apply a linear analysis, your loads have to be constant, so you only have one type of load, and the load only moves in one direction. It does not change in any axis. So if it's going down the y-axis, it will stay in the y-axis. Now think of this: if your part starts to bend or starts to move, or start to rotate away from that y-axis, now your loads will still maintain that y-axis and push your part straight vertically, as opposed to factoring in that horizontal movement. And the fourth criteria of a linear analysis is that linear material property. So it holds on to Hooke's law. Now, Hooke's law itself is an assumption. It's a very good assumption. It's worked well for many applications, but it's still not real. It is simply an assumption. Now, when it comes to nonlinear analysis, you can start to analyze model stiffness that changes. So even if the bend or rotation is large enough to change the stiffness of the part, that can be taken into account, because each of the analysis is broken down into smaller iterations. So it will run each iteration independently with the change of calculating the change of stiffness that's involved. This ties into the arbitrary displacement and rotation. So we don't have to worry about too much displacement or rotation in our part. We can allow it to move as it should due to the forces or pressure or loads that's being applied onto it. Third is the variable load. Now, the reason why variable load cannot be done in linear but can in nonlinear is because of the iterations. Because each iteration is run independently, if the load changes at, say, the third or the fourth iteration, it can account for that without having to simulate the loads from the first and second iteration. And the fourth is the actual material property. So if the material is yielding elastomer type of material, so if you have a rubber type of material, if you have a material that snaps, all that can now be considered with a nonlinear analysis. So we've talked a lot about stiffness in that first slide. So what really is stiffness? So stiffness is the property of a part or assembly that characterizes its response to the applied load. There are three primary factors that can affect the stiffness of a part. The first is the shape. So an I-beam versus a channel beam, even though it might have the same weight, it might have the same material, it can have different stiffness because of how the material is, the shape is distributed. Secondly is, of course, material. So different material will have different stiffness. So it can have the same type of geometry, the same shape, but even a slight change in material, even a material within the same class, can have different stiffness properties. And third is part support. So if you're not dealing with just parts, if you're dealing with now assemblies, you have to consider all the different parts being mated together. And when all these different parts are mated together, they are reacting to different stiffness of each part. Now, if every part has the same material, then maybe you might be able to get away with that. But now if you're dealing with different material, different stiffness, and these parts are touching each other, moving, and reacting to each other, then you need to consider nonlinear analysis. So when is a system considered nonlinear? So I promise there's not too much equations in this presentation. This is going to be it. So the system is considered linear when you have your stiffness matrix, multiply that by your displacement matrix, and that equals the forces. However, when the stiffness matrix and the force is no longer constant, the analysis is now considered a nonlinear analysis. So the new equation for a nonlinear analysis is your stiffness matrix is a function of your displacement and your unknown displacement and your forces, the external forces vector. Right? Okay. So by the way, if you have any questions during this presentation, feel free to type it in to the questions panel on GoToMeeting, and I'll answer them as I move along. So what about nonlinear analysis? So as I had mentioned at the beginning of this presentation, is that every analysis problem can be performed as a nonlinear study. And there are three types of nonlinearities. One is geometric, the second is material, and the third is the boundary contact. Now these nonlinear problems can exist independently or in parallel with each other, or even all three for that matter. So let's talk about the geometric nonlinear condition first. So this is caused by a large displacement or rotation on the overall geometric structure. So this is criteria number one. We are breaking that condition or that requirement for the linear analysis. Now if you have a part which is starting to deform in a direction away from the forces being applied, then you automatically should consider the nonlinear analysis. So let's go ahead and take a look at an example within SOLIDWORKS of a geometric nonlinear example. Okay, so here what I have here is a hose clamp. So if you saw the picture here, this is what it looks like. Clearly we've removed this part and we're just left with this, and we want to see the rotation of this part due to some force being applied to it, right? So what I've done here is I've actually created two types of analysis. I've created one, the linear analysis, and secondly I've created the nonlinear analysis, so you can actually see the difference when you run this with these two different types of conditions. So the way this analysis has been set up is we have it fixed on one side. So we have that face completely fixed. And on the other side, as opposed to creating a force to create that rotation, what I've done is I've actually just created a rotation condition of 6.25 radians. So that will give it that rotation. It will basically move this face in 6.25 radians about the y-axis. So you can see this is the y-axis right here, and if you look in under the fixtures on a flat face, you select the face, and we have a rotation 6.25 about y-axis. All right. Okay, so now you'll see again there's no external load applied to this part. So I pre-ran this analysis, and if you take a look at my stresses, you'll see that the part seems to deform incorrectly. And even if you look at the displacement, it seems to have stretched the part out and it has moved down this way. And if you look at the animation, you clearly see that it is giving you some weird reaction based on the translation that was created. Now, you might stop and ask, hey, wait a second, you didn't even apply a load in this case. You applied you actually applied a rotation, so shouldn't the part rotate? Well, not necessarily, because when you run a linear or any type of simulation for that matter, and you create a rotation or a displacement, what the software really does is that it tries to simulate artificial force that moves the that selected face in the proposed direction. And that's how it will give you the stresses based on some artificial force that it has tried to use to move it in that direction. So in this case, there is a force being applied onto this part. It's just that we can't see it. And what really happened here is that as opposed to creating a force which moves in this direction, it created a force that comes straight down, and it pushed the part all the way down here. So as opposed to having the force change as it rotates, it was not able to do that in a linear analysis. It just goes in one direction. Again, this is the second criteria that we talked about, or the third criteria we talked about earlier. Loads are constant and in single direction, so it goes in one single direction. Now let's take a look at the nonlinear analysis for this portion. And again, nothing was changed here. Everything's the same, but we've invoked the nonlinear analysis. And just to kind of show you real quick how we would do that is if we go into new study and we select nonlinear, you'll be able to select either static or a dynamic analysis. And this is basically a nonlinear analysis. And what differentiates a nonlinear analysis and a linear analysis is that under the properties, so I just right-click that top study and I say properties, you will see that now we have a stepping option. So as I had mentioned earlier, nonlinear analysis runs the simulation in smaller iterations, in smaller steps. So it runs each step or each iteration independently. This is what controls it. So you have to give it some time, so a start time and an end time, 1 second, 2 seconds, and you can even say a time increment. So you can either say you can either apply a time increment. So if I put 0.1, that would have been 10 steps, or I can even say auto stepping. All right. So in this case, let's take a look at what I've set up here for this nonlinear analysis. Is that I've set it up as 0.01, so there's going to be 100 steps for 0 to 1 second. And if you take a look at the results, you will see that we got the intended result as described. Now, if you take a look at the displacement, same thing. And if you try to animate this, you will see that the rotation moves as intended. Very nice. So just keep in mind, as this is rotating, you will see that the plot steps and the time that we set in our properties are showing up here. So what's even nicer about having a plot step is that if you go into either the stress or the displacement and say edit definition, you can actually show the displacement or the stress at a given step. So let's just say I want to see what was the displacement at halfway through, so at 0.5 seconds. So this will automatically recalculate for me to 50. And when I say OK, you'll see that that's where it was at 50 seconds. This is probably more applicable in a stress environment, because we want to see what are the stresses as the part is deforming. And in this case, rather than setting a second, you can even put in a plot step. So if I say 30, that will automatically update for me as well. Say OK, and you will see at 0.3 seconds, the stress that I got for the part is as follows. All right. So the next example, or the next type of nonlinear that I wanted to talk about is material nonlinear. Now this is a stress strain graph. I think a lot of you have probably seen this at least once in your lifetime. Essentially, this is the linear zone, so linear and elastic, and that's your yield strength right there. Typically, this is your linear zone right here. So anytime you're running a linear analysis, that's about all you are applying for your material in your simulation. All these areas is completely disregarded. In a linear analysis, what happens is this graph will just be extended in a linear form, and essentially everything past this dotted line here is garbage. It's not real value. When it comes to nonlinear analysis, this is what we call as the nonlinear zone right here. So this small area right here, typically in a nonlinear analysis, it is still considering in most cases the values are very close to the linear line that you have. However, it's still not exact. So although the linear analysis considers all analysis up to yield strength, you might be missing information in this elastic area right here. So this is something else that you should consider. If your parts are close to yield strength, then you might want to start considering nonlinear analysis. So let's go ahead. Well, before I show the example, I actually wanted to show you some of the material that SOLIDWORks provides. So when it comes to nonlinear materials within SOLIDWORks, there are 5 main types of material. So you have your elastic, elastoplastic, superelastic, linear viscoelastic, and your creep materials. Now under elastic, you will get your linear elastic, nonlinear elastic, hyperelastic, and then hyperelastic, you have your breakdown for these 3. Now really, when it comes to nonlinear, this is the biggest challenge in picking the right material, and not only picking the right material, but creating the right type of material, or what category it falls under, because that brings up extra properties that you can input, which gives you better results. Now again, when you run into nonlinear analysis, a lot of people try to move away or shy away from it because they think that it might be very difficult, very involved. However, in my experience, this is probably the most challenging part. And essentially, when you run your nonlinear analysis, as long as you've run enough research on the type of material you have, by using this chart, you'll be able to fall under these categories right here. And when you do fall in these categories, if there's some properties or you need to find out more information about what's the difference between flat score or octant, SolidWorks CAD Dimensions tech support typically will be able to help you with things like that. So again, it's not as challenging as what many people perceive it to be. So let's go ahead and take a look at an example here. And this is a really good example. I particularly like this example because I have not met a person that has not used a paperclip or abused a paperclip, I would say, because you know, it's just a fun thing to play with. You bend it, and if you think about it, when you use a paperclip, if you bend it a little bit, typically it goes back to its original shape. But if you bend it far enough, it stays in that prescribed shape. So I don't think paperclip makers are using simulation to test their paperclips. However, this is a great example because this allows us to see what happens when the part passes that yield strength point. So let's take a look at the next example here, paperclip. So again, I have my two analysis. I have my linear analysis and my nonlinear analysis. Now my linear analysis, very simple. It was fixed on one side. So imagine you're holding the clip right there that highlighted, the one that's highlighted in blue. You're holding it there, and you are holding with another finger this face right here, and you're just pulling it and you're just bending it to open up the clip. And you're applying 1 newtons, so that is more than enough for a small paper clip. And if you take a look at the results that we got here, you will see its deformed shape. Now this is great. This is great information in a linear environment. You got this information, very good. However, what if you want to know what happens when you let go of that 1 Newton force? What happens after that? That can only be done in a nonlinear environment. So let's take a look at creating this for nonlinear. And the difference in this example is that as opposed to just applying a 1 Newton force, I created the force using a curve, and a curve of force versus time. So if we view here, just show you how the values are input. So for 1, the seconds, so 0 second, 1 second, 2 seconds. So the analysis is going to go for 2 seconds long. And y is the multiplication of your force. So if you are putting in 1 newtons, at 2 seconds it's going to be 1 newtons, and then at 3 seconds it's going to be 0. Now the only reason why I'm mentioning this is because it might be a little bit confusing because I'm using 1 here and 1 newtons. So if I'm using, say, 10 newtons, this would still be, and I want to apply 1 newtons, it will be 0.1. So it's a multiplication of the force that you're using. And you can see how the graph here looks. Now because of the direction of the force, you can see it's actually in the reverse direction. And if you view the graph, it goes opposite to how we input it, which is how we want it. And you can see at 0 second and at 1 second, it's the full amount of force is being applied to it, and after that 1 second the force is let go, and at 2 seconds it's at 0. So we want to see what happens from 1 to 2. So again, if you select on the stress here, and if I edit this, you will see this is at 1 second. So this is when that force is at full capacity. So 1 Newton is being applied to the paper clip here, And watch what happens when I move this to 2 seconds and I say OK. See, it falls back down and the highest force is only at 125. Now if you take a second here and compare those results, so if I say compare results of the two stresses, you will see that for the first linear analysis was 489 at its final point, but here is 125 at its final point. So this is from 1 to 2 seconds. This is at 1 second. That was the final force being applied to it. Now we can also view this from a displacement standpoint. That's not linear. Displacement standpoint, and I will say animate this all the way. And you can see how that reacts, and there is a kind of a snapback or move back after the force has been let go. All right. Let's take a look at the PowerPoint. So the third example that I'm going to talk about today is the boundary nonlinear condition. So this again results from the changing nature of the boundary conditions involved in the analysis that come into contact during movement or if it's already in place. So in this example, this picture right here, you'll see that this says a beam here and there's a force being applied. If there was no restriction, this beam would probably bend as expected. However, due to the boundary here, the displacement or the bend shape that you get for this beam might change significantly. Now, one or two things can happen here. If this part has a stronger material, it might just break this piece right here, right, very thin wall. Or if this part has a stronger material, then this beam might start to bend more vigorously. So the bend might be more what do you call it? The angle of the bend might be higher as opposed to if there was no restriction here. All right, so let's take a look at an example that I have here, and this is for an O-ring. So this is something that is being done quite a bit. I know a lot of engineering applications require O-rings to be used. So in an O-ring example that I have here, so the first example that I have, I'll actually just show you the model itself. You can see that there's just two plates and an O-ring sitting in between the two plates. And what I've done for this nonlinear example is I've used 2D simplification for the analysis. And in this analysis, I just want to show you a case where the boundaries do not really affect the O-ring. So if you look at the stress, all that was done here, again, there was no force. The force here is actually suppressed. There was only a reference movement. Well, this moved close that two plates, and we can see what the stress is on the O-ring itself based on the material that was created. Now, let's just say, for example purposes, this hole was significantly smaller. So instead of just touching the top and bottom, the O-ring is going to start hitting the side walls as well. So now the boundary is going to play a big role in how this O-ring is going to close that these two plates here. So in the first example I have, I'm going to use the same material. It's a custom material that I used from my first example. And you'll see that the O-ring groove is a lot smaller in this case. And if you take a look at the stress, you'll see that the O-ring has completely closed off the hole, and you have some stresses being created, stress concentrators on the part itself. Now, this is very important to consider because in this case, the analysis actually worked. So the O-ring, you were able to close the two plates, and the O-ring is still in place. The O-ring didn't give out. This is very good information to know, what kind of stresses is being applied to that O-ring. So in this case, I could use a probe tool, possibly probe somewhere in the middle, and it gives me a 600 psi. So now maybe a secondary analysis might be involved here, where you're testing that O-ring for 600 psi to find out if it'd be able to withstand those type of stresses on it. Now, in the third example that I have here, I have used a different material, EPDM 60 durometer, and in this case, this rubber is a lot stronger than the previous two examples. So essentially what would happen is that if you were to try to close these two plates, this rubber will actually push back on that top plate. So if you look at the stress, you will see that it never actually comes together, and I have all 0, 0, 0, 0 here. Now, if I were to run this, again, it actually took a little bit of time, took about 2-3 minutes. However, it actually stopped. And if you look at the stress results itself, the analysis stopped at 0.19 seconds, but the properties that we set was for a whole 1 second. So why did it stop at 0.19 seconds? Well, the reason is because the material has buckled before it was able to completely close up. So essentially, that at the point where the rubber starts to hit the side walls, the analysis was not able to compute anymore, and it stopped. So this is a great way to evaluate if that rubber might be too hard for these types of analysis. So in this case, you might want to open up that groove a little bit more and retest your parts, or even change material. So very good information. It just doesn't stop the analysis and says good luck, right? At least it gives you some information. And actually, when you run this analysis, when it stops, it will tell you that the rubber has the part has the component has buckled due to the displacement that was set in the analysis. All right, so how can nonlinear analysis help you build better products? Right, that's the main question of this presentation. Well, nonlinear is nature. So linear analysis is simply an approximation of nonlinear analysis. So essentially, when you are running your simulation, not only it's considering all the assumptions that you have put into your analysis, you also are approximating a nonlinear type of analysis. Of course, if your linear assumptions differ too much from reality, you can get misleading information, which can cause your, it might say your part is failing when it's not failing. Using nonlinear can reduce over-design. So nonlinear analysis may show that some yielding is acceptable. So in a lot of cases, before virtual testing, typically people would over-design. Now, we were able to move away from over-design by running now virtual simulation. However, with nonlinear analysis, you might be able to dive even deeper to those results, and maybe even use your factor of safety in that case and get even better results. Saves money and time. So again, it's kind of a catch-22 here, because a lot of times people say, well, nonlinear analysis takes more time, and of course it costs more money. However, on the back end, it actually might save you money and time, because the better understanding you have of your parts and how the forces are applying, causing the type of reactions on your part, you might have much better iterations and changes to your parts. And of course, all these leads up to better understanding your product, reaction to external forces, leads to better innovation. So next time, before you run your simulation analysis, ask yourself these questions. Does the problem involve only linear characteristics? That is, does it have excuse me, no nonlinear material properties, large deformations, or motion? Secondly, are all the loads static and accurately quantified? So if your loads are starting to move in a different direction, now the load that you apply might not move in a different direction. However, due to the displacement of your part, that load might require to change directions. And of course, do you thoroughly understand how the simplification of the static stress analysis affect results? So, in no way that we should take away from static analysis. It's a great part of simulation. It's a very good approximation. However, without really understanding some of the assumptions and simplifications that's being applied, the results might be crude, or you might be get misleading results. So if the answer is no to any of this, then you are a candidate for nonlinear analysis. So I'm just going to open up the floor now for any questions. So it's about 12:42 right now, so I'm going to wrap up soon. There's no questions right now. Again, feel free to email me any questions at sashi@catdimensions.com. Oh, actually, I do have one question. One question, actually. So, are you saying the analysis doesn't know how to handle the EPDM O-ring touching the wall of the groove? No. So what happened in that case is that due to the material, it's a very strong rubber, the stress in the part was very high. It was actually not able to completely squish that groove. It may have caused the part to crack. It may have caused a very high stress, maybe even a very high stress concentrator on the plates that was being used to squish that O-ring. So that's the reason why it stopped the analysis. So it's not that the simulation was not able to that cannot handle it. They actually handled it very well, and basically told you that O-ring is not going to work in this type of application. So again, in that case, you might have want to open up the groove a little bit and rerun the analysis. That might have worked, or change the material. So as I showed you in the example, the same type of groove with a different material was able to work just fine, and it actually closed it. The stress was very high in this case. However, in this excuse me, in this analysis, the stress might have been too high that it's actually causing this part or this part to buckle, and that's why it failed. Good question. Any other questions? All right, so no other question at this point. Again, if you think of any questions later today or tomorrow or whenever it is, please feel free to email me at sashi@catdimensions.com. Feel free to call us at 877-223-4255 as well. And again, visit our website, www.catdimensions.com. A lot more lunch and learn, such as the one that we had today, that's pre-recorded, that's sent to our website, so you can catch it over there. Thank you. Really appreciate you guys taking time out of your lunch today to join me, and I hope to see you in the next lunch and learn session.